So in this video, I'm going to talk about non-free fall again. Let me show you this video. When we were in class, we usually do this demonstration together. So here is our good old campus, Santa Monica College, in a science building. And my previous students are in the second, third floor. They have a white ball. White, it's not white actually, it's a yellow tennis ball, and then a basketball. So it's a different sizes ball. Which one do you think is going to experience the bigger air resistance force? Do you think the basketball or tennis ball, are they going to have the same air resistance? If it's not, which one is larger? Right, so the basketball is going to feel the larger air resistance because of the frontal area, right? So if you drop the tennis ball and a basketball without the air resistance, if you don't have any resistance, tennis ball or basketball, they should both fall and then hit the ground at the same time. But with the air resistance, what would you expect to be? Which ball, if they're both dropped at the exact same time, which one is going to hit the ground first? Guess. Let's see. So here, I can start from the beginning. So they're going to drop the balls. Yeah. So which one hit the ground first? Tennis ball, right? Let's see, around here, you can see the tennis ball starting to go. So in the beginning, even the beginning, the tennis ball actually was dropped a little bit later. It's hard to control, especially if there are two different people that's releasing the ball to be exactly at the same time. So maybe I should ask one student to let go at the same time. But I asked the two students separately. So they might not have let go the ball at the same time. So obviously the basketball was falling first. It went, sorry, it went first, and then the tennis ball was behind. But you see the air resistance on the basketball catching up, building up more, and the tennis ball's air resistance is smaller. So at this point, tennis ball is already ahead of a basketball. And then, oh, it's too bad I don't see it. I hope you guys don't see this bar. Probably will though. So it's actually the tennis ball that hit the ground first. So yes, the frontal area matters in this case. In this video, I want to talk about this motion. I showed you the different video, but it's the same thing. Let me see. Let me share here. I want to talk about including the air resistance, the ball that's been thrown upward and coming back down. Now we're going to include the air resistance and analyze the motion. So here, she's going to throw up a ball upward, right? The ball is going to go up, reach the maximum height, come back down. Good. One more time. Go up. So first I'm going to talk about the ball that's go up and at the maximum height, and the ball that's coming back down with the air resistance. Okay. So I'll share the note. Okay. So let's talk about when the ball is immediately being thrown upward from the hand. So you have a hand like this, and you want to throw the ball upward, upward. So when the ball is on the hand, the normal force is going to be larger than the gravitational force and push up and up and up. Once the ball is let go from the hand, so now the ball is completely in air by itself. So let's see. Let's start from here. The ball is going to be completely in air by itself. And then it's a little bit up, still moving upward. And then moving upward still. Okay. Then how about when it's at maximum height? And then now the ball is going to come back down. What happens to the forces, including the air resistance? What happens to the... I think I can draw the circle if I do this. Yeah, so I do that. What happens to the ball? The net force acting on it, and that. So much better. So let's see. Immediately after the ball is let go from the hand, either way, you're always gonna have gravitational force vertically downward, right? So you're gonna draw the gravitational force vertically downward. Ft, Ft. But want you to be careful though. Here on the left side, ball is moving upward. This is the direction that ball is moving upward. Moving, the direction of motion. Right? So, which direction is the air resistance applied when the ball is just being thrown? Which direction is the air resistance, you think? Air resistance is gonna be pointing downward, right? That's because motion is upward. So it's the air drag force that don't like the motion that opposes. So it's going to be pointing downward. So then the acceleration is larger than g, downward direction. So, and then initially, so here, and net force is Fg plus R, downward. You're going to have a bigger than a gravitational acceleration, and the net force is downward. This is at the initial speed. When you throw in a ball, you have an inertia that wants to go upward. But the only force applied, well, you have a gravitational force and a resistance that's trying to pull it down. So you're going to have an increasing in speed, decreasing speed, or constant speed. Speed will be decreased. If the speed will be decreased, what would happen to the magnitude of a resistance? Air resistance will be less, right? So we're going to have in the second step, we're going to have a gravitational force that's, gravitational force is the same. It doesn't change. Just there. It only depends on the mass and the gravitational acceleration. So this is Fg. But R, the air drag force, will be smaller. And which direction it should be pointing? Still downward, because it's still moving upward, right? So the air resistance will be somewhat, little bit smaller than the initial one. And acceleration will be still bigger than G, but not as much. Not as much. In case of here, acceleration, this is larger than this. Acceleration is decreasing, but still it's downward. Then again, over here, we still have the same amount of gravitational force. That doesn't change. And the air resistance, direction of air resistance is going to be up, down, or the what? Still downward. And the size of the arrow, the air resistance is going to be even smaller because it decelerates. It slows down even more. So R is going to be tiny enough. So the R gets smaller and smaller. Air resistance becomes smaller and smaller as it goes higher and higher. Still downward. But smaller and smaller. What happens when the ball is at maximum height? Does the ball in a maximum height? What's the force, net force? Do we have a gravitational force applied? Either way, it's at maximum height. So that's where the turning point is. So no matter what is speed? Speed is 0, right? At its max. So it decelerates, slows down even more than without the air resistance, because you're going to have an air resistance that's pulling it downward more. Not just the gravitational force, air resistance together is going to pull down. So it's not going to reach as high maximum height as if it's in vacuum. So when you have air resistance, you don't go as high. Then do we have a gravitational force when the ball is at maximum height, when the speed is 0? Yes, gravitational force doesn't turn off. So gravitational force is still there, doing the same thing. Now it wants to change the direction, other direction, right? So gravitational force is mg, mass times gravitational acceleration. It doesn't change. So it's there. How about the air resistance? That's right. The speed is 0, right? Speed is 0. So when there's no speed, air resistance is 0. So here we say R equals 0. No air resistance. R equals 0. No air resistance. So the net force acceleration is G, net force is Fg at that moment. Then what happens when the ball is starting to come back down? We're still going to have a gravitational force, same, vertically downward. Now, what is the direction of a resistance? A resistance force now, since it's going to start coming back down, right? Now the ball is going to start moving downward. Moving down. Now it's going to move down. So the direction of air resistance will be now upward. But since it reached the maximum height, the speed was 0, it's starting to come back down. So it doesn't have much speed yet. So the amount of air resistance is still small. Then, as it goes down, so then in this case, the acceleration is going to be bigger or the same or the smaller than a g. Acceleration will be smaller than g. And here the net, how to find the net force. Net force, now the net force here is Fg minus R. Then later on, gravitational force still the same. Then you're gonna have an air resistance, still upward, but now it's starting to build up. The acceleration is even a lot less than g. As it goes down, it's gonna, acceleration is less than g, but still, let me see, acceleration is still pointing downward. Downward. Right? Acceleration is still downward. So, but it's slowing down. At one point, this R might reach, may not. It may hit the ground by then, or it may be still in air. But if the R reaches the same amount as the gravitational force, then this ball is going to be in terminal speed, constant motion. It may hit the ground before then. So if that's the case, it's just going to be acceleration will be less than g throughout. And it might be just 0. We don't know. Or A can be 0 when net force becomes 0, which in this case net force is Fg minus R equals 0, downward. All right, so I want you to be able to discuss and analyze the direction of air resistance of the ball that's been thrown upward, acceleration, be able to draw the force vector diagrams, acceleration, discuss net force when the ball is going up, when it's at maximum height, and when it's coming back down. All right, so make sure you can do and analyze these motions. Okay, so I'll see you in the class.